Hi, welcome back. This topic today is on the difference between population versus sample data and on descriptive statistics. Okay, so descriptive versus inferential statistics. If you look at almost any stats book, right, the early chapters are concentrated on descriptive statistics, which, if you see the first bullet point here, describe data. All right, it's the process of collecting, presenting, organizing, and describing data. And that description can be visual with graphs, histograms, and pie charts, and bar graphs, and line charts. It could also be numeric: the mean, the median, the mode, the variance, the standard deviation, the interquartile range, the range, the max, the min, these kind of things describe data. Okay, but you're not at that point using data to say anything, to infer anything about something unknown. And so inferential statistics, the second bullet point, is usually made up of the last half of any stats book, at least at the undergraduate level. and inferential statistics is about drawing conclusions or making decisions concerning a population based only on sample data, right? And so if you think about any sort of general election in the United States, when we're moving up to a presidential election, let's say in every 4 years in November, almost every other day up until election day, there's a poll conducted by Gallup, CNN, a host of credible polling agencies will do this, and a lot of people actually synthesize all those together to come up with kind of a poll of polls. But anyway, when a poll is taken out of, I don't know how many registered voters you have, but let's say there's 200 million Americans that can vote, just for instance, only about 1,000 or 1,200 people are asked in a given day who they're going to vote for. And from that, okay, the headline of a Gallup poll or a CNN poll is, that 70 or 43% are predicted to vote for Mitt Romney in November, for instance. And so that sample, which is in absolute terms pretty small, 1,200, is actually a reasonable sample size to infer something about millions and millions of people. All right, if that sample is taken correctly, so it has to represent the population of interest, which is voting Americans. And so some people find that actually striking. That's only 1,200 people are used to infer something about the entire country. But there is sound statistics behind that. And once we get to the chapter on sampling distributions, that should be clearer. So right now we want to talk about the difference between population parameters, and I have both of those, PP there in blue, and sample statistics. So PP, SS. Keeping these separate is important. Most of this or much of this may be just intuitive, but humor me as we go through some of these slides. So here's a CBS News poll way back in 2005. The majority of Americans reject evolution is the headline. And so you see these three results. God created human present form. You see 51% of respondents say that. 30% say humans evolved, God guided that process. And 15% say humans evolved, God did not guide the process. And so the 51% that say God created humans in present form is extrapolated to that headline of the majority of Americans reject evolution. So the question could be, what's the population of interest? Or the first question. The second question is, what's the sample? So what's the population of interest? Well, let's see. Down here in italics, it says this poll was conducted among a nationwide random sample of 808 Americans interviewed by telephone. So a sample of 808 Americans is used to extrapolate what the country thinks. However, it's not specifically spelled out here, but my guess is that they're not. The CBS isn't interested in what my three-year-old daughter thinks about the evolution of humans. And so my guess is that their population of interest is adult Americans. All right, and if you look into the fine print of their study, you may get some more information there. So I would say that Americans or adult Americans, and their sample of course, is the 808. Okay, so we're looking at millions upon millions of people in the population and 808 people in our sample. All right. Before we move on, I want you to keep in mind that we're going to be learning to be statisticians step by step. So early on in this course and in the early chapters of any textbook, you're going to know information about the population. Okay, unlike here, which is a research question, CBS conducted the poll because they didn't know the answer. They didn't know what the population actually thinks about evolution, so they asked 808 people. But unlike that, in bullet point 2, although we aren't likely to know population parameters for interesting questions, we're going to start this course knowing that information. And the reason is that we want to understand what distributions of data look like, okay? The kind of data that we're after, the properties of a population, so that when we're taking a sample, okay, we have a good understanding of what's going to underlie that sample. And this is going to be important. And again, Chapter 8 plays a role. The sampling distribution is when you take multiple samples from a population. All right, and lo and behold, it turns out that we don't even need to know what that population looks like, okay, because of, some things that rely on, namely the central limit theorem. Okay, but we're going to start the course knowing what the population looks like, and then we'll start taking these things away. All right, that's that third bullet point. So descriptive statistics, in general, what the data looks like, and this is not just graphical representation of data, it's also numeric. So when you describe a distribution of data, when I say a distribution of data, don't let that term distribution scare you. That just means if I'm organizing data, you can think of if I had a column of data in Excel, I don't know, 200 observations, and I rank them from smallest to largest, so I organize it in that fashion. And then let's say I created a histogram, just a picture of that data, right? Well, the act of doing that, I could find that histogram could give me a general shape of this data, okay? And the shape is going to be important. In my example, there are normal distributions, that bell-shaped distribution, right? It's symmetric, and the bell-shaped is the normal distribution. The center of the distribution is something that we're going to be interested in. We're actually going to concentrate on the mean, the average. But there are other measures of central tendency. The median is one, and that's often used. The mode is less often used because often the mode has nothing to do with the center of a data set. It could, but often it does not. And so we will neglect the mode in this course. So we have the shape. We want to know what the shape looks like. We want to know where the center is, the measure of central tendency, and then how much the data vary. So the variability or variation. And our chosen metrics are going to be the variance and the square root of the variance, which is the standard deviation. The standard deviation tells us how much on average our data deviate from the mean. Okay, deviate from the average value. So let's look a little bit at these three. Measures of central tendency first. So we're going to go to the second bullet point first. The mean, the mode, the median. These things apply to both population and sample data. So they apply to the 200 million Americans of the population and the 808 Americans in our sample from our previous slide. Okay. Moreover, comparisons between these, namely the mean and the median, comparisons between the mean and the median can give us an understanding of how the data are skewed, or which direction they're skewed if they are. In this case, this is and we'll see this graph again. This is a histogram for semester grades, and the bars of the histogram are just spaced out for no reason. And these are semester grades, so it doesn't go to 0 on the horizontal axis, but it does go to 4.6. That was what somebody earned for the entire semester. But you see that most of the data are, above 55 or above 60. Most people pass, the vast majority. And this is very typical of grading distributions. Grading distributions are very seldomly normal. They're often what this is left skewed. And in fact, we could tell that this data set is left skewed by a comparison of the mean and the median, and we'll do that in a few slides. All right. And so this kind of smooth distribution, this red line, is an approximation, and that's the kind of thing that you'll see in most textbooks, you'll see in my graphs, is that you'll see these smooth lines, and these are, for the most part, you have to think of those as approximately smooth. That allows us to use Z and T tables, which are basically integrations under these smooth distributions, so we can find areas under those curves. The mode is the most frequently observed value. This is the last slide. I'm going to talk about the mode. It may not exist as a problem. There could be multiple modes, and it often doesn't reflect the center. The mean is going to be our chosen measure of central tendency. That's not to say it doesn't have problems. We talk about it, the last bullet point here. It's sensitive to extreme values. Often when income is reported at a country level, let's say, it's the median income that's reported, because the mean income takes account of all the values. It takes all data into account. So it takes Billy Gates' income and my own income, puts it all together with everyone else, divides by the total number, and you've got your average, your mean. So it's useful, and it's our chosen metric because it uses all the data. It doesn't dismiss anything. But it is sensitive to, with income, extremely rich people. Okay, there are a lot of people who are on the left side of a ranked horizontal axis, but the 1% hang out way on the right. And here's an example of extreme values, or I don't know, it's a picture of what's the science is the flaw of averages instead of the law of averages, I guess. So this guy's walking around, he's in a suit going to work. He sees a pond, a little puddle, I don't know, a pond. It says an average depth of 3 feet. And this guy, I don't know why, maybe he's wearing, Wellingtons or some sort of boot there that's waterproof, but he thinks, all right, 3 feet? I'm 6 feet. I can walk through that whole thing, no problem. But lo and behold, as he gets to the center, it's that the average is 3 feet. So the middle turns out to be an extreme value, well over 6 feet, and this poor guy drowns to his death. That's right. Poor guy dies. Flaw of averages. The median is the center of an ordered list of data. So rank your data from smallest to largest, for example, and whatever the median is, 50% of the observations lie on either side. So it's the 50th percentile. All right. Of course, a percentile, I'll remind you, divides a data set into 2. The values don't matter. Doesn't matter what Billy Gates is earning or any unemployed person is earning. It's whatever happens in the middle. So it's resistant to extreme values. But it doesn't give us any sort of data set. It's a singular value. And if you're using the median, then the measure of variability, okay, is going to be awkward because we want to measure variability relative to something, and we have to measure it relative to the mean if we're going to use standard deviation. And so the median doesn't offer that same kind of linkage to the variability of data. So back to this graph, I said that this data set is skewed left or left skewed. You know that by whichever way the tail kind of drifts off to. But it needs to be the case, it's necessarily the case, that if the mean is less than the median, then you have a left skewed data set. And lo and behold, the mean is less than the median. All right. And this is kind of the opposite direction of an income graph. This is a grading distribution. Most people are up by the C's, B's, and A's. Some people walk away with a 4.6. Hardly, it's hard to earn that. but it's possible. You just have to almost do nothing. Anyway, left skewed, like almost all grading distributions would be. So, measures of variability. You can see that these two graphs, these two graphs have the same center, but they have different variability, different variation. And so we're going to condense that into the variance and the standard deviation. Okay. In this case, they have the same mean, but they have the same different variabilities. Now, if you're comparing populations or samples, I mean, often you'll have different means and different measures of variability. And so if you want to compare data that have different means, you want to control for that. But before we get to that, the variance and standard deviation. So the definition of the variance, the average of the squared distance of the data from the mean. So the mean plays a role. So right there we know that the variance, because it relies on the mean, is also affected by extreme values, also affected by Billy Gates' huge income. Or, for grading, the slacker's 4.6 percentage grade, which is amazing. Now the variance, again, is the squared distance. The reason we square these things is because if you didn't, then you'd have equal deviations below the mean and above the mean, and it would cancel each other out. And we know that because the mean exactly balances the data. So we have to square these bad boys. So if we're talking money, we'd have money squared, or grades would have percentage grades squared. And so that's awkward. So to get it back into the units of the problem, we take the square root, and we're in the standard deviation realm. So the standard deviation is kind of the workable form of the variance, but they give you the same information. Okay, if you have one, you have the other. That's it. Again, sensitive to extreme values indeed. The formula the formulas I have handwritten here. I've actually handwritten them because throughout this course you're going to see me writing, and it does help to kind of get used to my horrible penmanship. And so this is kind of the first slide where you can get in on it. But I do use the pen to do some writing and drawing of distributions throughout. Anyway, some notation, some reminder notation for summation notation rather. Okay, so I have 3 examples here, and the first example, and hopefully this cursor shows up in the video, I've got X, which is income. Okay, and I, when you see I here, XI, and sometimes we'll drop the I. Most of the time we drop the I. All right, but on your textbook you'll see it at the beginning, and they drop it too. But the I is just an index. This is like, well, you've got, let's say we're talking about a class of 60 students. You'd have student 1, 2, 3, all the way to 60. So capital N would be the population size in that case, 60. And this says, this capital sigma says to sum all of these X values from I equals 1 at the bottom to N at the top. So this just says sum everyone in that data set. This one, you'll notice that I've taken away the superscript and the subscript because that's often how you see it. So it's implicit. Now it's implicit that I'm going to be summing from 1 to N from everybody. But first I'm squaring these terms. X squared. So I'm taking the income of me and squaring it. The income of you and squaring it. And then summing all those squared terms. Now the difference between 2 and 3 is important, that's why I do this exercise, is that here the parentheses are on the summation. So this is telling me not to square individual terms. This is telling me to sum all of the X values like you did in 1, and then square that sum. So 2 and 3 are totally and dramatically different. So beware. Now the formulas, which use the sigma term. You'll notice that I've dropped the superscript and subscript from the sigma term, and you should expect it to be like that. The variance is following, so you'll see that I have population formulas and sample formulas. Okay, and you have to learn these. not only do you have to learn how they're used, but what they mean, and notice the difference between the notation. Sometimes I'll say the standard deviation of the sample is blah, blah, blah. And sometimes I'll say S squared is blah, 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 which would be the variance in that case. But S is, blah, blah, blah. So you got to be pretty sharp with these things. All right, so we'll start with the population, left-hand side. The variance of the population is denoted by lowercase sigma squared, lowercase. All right, this is the uppercase. And it's going to be the average of the squared deviations from the mean. And so we have mu here. The Greek letter mu is the population mean. X is income, or whatever X is, doesn't matter, it's just a placeholder for the variable. And so X minus mu is each deviation from the individual value relative to the mean. In parentheses, I'm squaring this. So this would tell me to sum all these squared values and then divide by the total population size. And that would give me my variance, but it would be units squared. The standard deviation is simply the square root of that. So it's sigma, lowercase sigma. Now if I have sample data, and again we've already talked about the difference between population and sample, then my notation is S squared. So notice we have Greek letters for populations, and we have these Roman letters for our traditional alphabetical letters for samples. That we'll maintain that throughout the course. So S squared is the sum of the deviations between the mean, but notice it's not the population mean, it's the sample mean. X bar is our sample mean. X bar is just the sum of all the data values divided by little n, and little n is the sample size. Notice the difference between little n and big N is just capital and lowercase. So the numerator looks the same, and it'll actually be, except for the substituting the Greek letter for the X bar, but it's the denominator that's different. And the denominator is n in the population, but it's n minus 1 in the sample. And the reason we do this is that we lose what's called the degree of freedom. So the denominator is actually called the degrees of freedom for this problem. And why we lose a degree of freedom is that we had n in our sample. So let's say n is 100 people in our sample. Well, we used that 100 people to calculate X bar. Okay? So we inferred X bar. We estimated the sample mean, right? Or the mean from the sample. Every time we take a sample and calculate a sample statistic from it, and then use that sample statistic in another calculation like we're doing here, we lose a usable observation. We lose a degree of freedom. All right? So if we then took our sample variance and plugged it into another formula, okay, to estimate something else, then we'd lose another degree of freedom. Okay? Now we don't have to do that with the standard deviation, it's just the square root of the variance. It's the same number. It's the square, it's the same piece of information. And so S is the standard deviation. This would tell us the average deviation from the mean of the sample. So why variance, why standard deviation? Well, I think I've covered this. I'm going to move on. Standard deviation is in units. And we're going to do a practice question. Pause the video for one moment. Okay. I think we're involved here. We're back on. Okay. Yeah, we're good. To give us a practice, some practice with the standard deviation and the variance, I have the box office earnings in millions of dollars rounded for the weekend of May 31 to June 2nd in 2013. Fast and Furious 6. Wow, 6, huh? Amazing. $35.2 million in that weekend. Now You See Me, 29.4. After Earth, 27.5 million. In Star Trek Into Darkness, 16.8. Nerdy movies is what we're dealing with here. Okay, so the question says, what's the standard deviation of this sample? So I'm just telling you it's a sample, okay? and it's pretty easy to work with. Ordinarily, if I'm doing this face-to-face in a classroom, people have calculators, and I try to make it very small. Now, with an online course, you have a little bit more, obviously, flexibility because you can use Excel, but nevertheless, I still have this 4 observations. Let me open up Excel, and you'll notice that, what's this? I'm using a Mac here, but I'm opening up Excel in Windows, and the reason is I'm going to use a tool called data analysis in a minute, and the Excel version of the Mac doesn't have it. It's just the sad reality. I'm going to open up the data set. Let's see if I can figure this out. I'm going to pause this for a second while I do it. Okay, so we're back. Here is the data set. Again, it's pretty easy to work with. And some calculations in Excel, very basic. If we want to calculate the mean, we want to calculate the variance of the sample, and we want to calculate the standard deviation of the sample. All right, extend this a bit. In Excel, we're talking about average is the method. The variance, if you go equals var, you have 2 options. var.p is the variance for the population. var.s is the variance for the sample. I've designated these 4 observations as sample data. And the standard deviation is, I could just take the square root of that, but you'll see that there's standard stdev.p is for the population, .s is for the sample. And so this is the these are the sample statistics for this. Now, I should say that what we're going to use in this class is this tool set called data analysis. All right, and once you activate it, and I posted a video on how to activate it. Once you activate it, it's there, and you click on it, and you can click on this tool. There's a host of tools here, but there's one called Descriptive Statistics, and you grab your data. I took a label, and you click Summary Statistics. That's all you need to do, and you've got, what do we get? 27.225, that's our mean. The standard deviation, these were our statistics were calculated, 7.68, yep, and 59.03, and there you go. This gives us some other stuff that we'll get into. Standard error when we get to Chapter 8. The median, if you're interested. The mode's not available. Kurtosis and skewness. These 2 are measures that have to do with the normality of the data set, how normal it is. Don't worry about that. The range is simply the min minus the max minus the min, and the maximum minus the minimum are there. Sum is the sum, and count is the sample size, 4. Okay. Now, descriptive statistics. This output, this tool, is only for sample data. It's only for sample data. All right. If you had a population data set, you'd want to just use the population tools or formulas. All right. var.p, stdev.p, because by default, the standard deviation of this is going to be divided by n minus 1. As in the variance as well.